Hello everyone, welcome to today's video. Today we're going to discuss 3 landmark OpenAI papers that introduced reinforcement learning from human feedback and showed us how we can leverage PPO to post-train and align a large language model to kind of follow a user's intent. Basically, how can we make this into a conversational assistant? Now, around the time these papers were being released, OpenAI was really hedging on the idea of scaling these large language models up, scaling these transformers up, feeding them a bunch of data, having them have a bunch of parameters, and just pre-training them with, again, a bunch of data. And this showed to result in really incredible text generation capabilities, language interpretation capabilities, right? But what these papers introduce is the next step forward. How can we make these models more human-like and have their intelligence be shown in a more human-like manner? And this is basically the precursor as well into reasoning and how we can not just have models that have incredible language capabilities, but how they can also reason and, answer logic problems, math problems, code, as well as a human does, etc. And I mean, you've seen recently the push on how important post-training is, how we've seen a GPT model recently solved an Erdos problem that was unsolved for hundreds of years. This is a mathematical problem. And additionally, how we're using large language models for coding tasks, right? All of that basically began and grew from these 3 papers. And let's get straight to it. Let me share my screen. And we're going to see basically how RLHF works in practice before building it next video. Just want to say, quick note, I haven't seen these papers in like 2.5 weeks. I'm really behind on these videos. So if I get tripped up, you might see a lot of edits in this video, but that's okay. We're going to start with the first paper. Well, first, let's overlook all these 3 papers, right? This first paper was released in 2019. It's called Fine-Tuning Language Models from Human Preferences. Second paper released in 2020, titled Learning to Summarize from Human Feedback. And 2022, titled Training Language Models to Follow Instructions with Human Feedback. You see a big common theme here. We are thinking beyond just supervised learning. How can we use a human's preference, a human's feedback, to align our models to follow a human's intent and a human style of thinking and receptiveness to answers and things of that nature? We spoke about this, and I kind of gave like a high-level overview and generalization of how RLHF works back in the reinforced video, which is the beginning first video of the series, and seeing how we can potentially use reinforcement learning to achieve these goals. We also talked about supervised fine-tuning, which is a step that takes place after pre-training. We're going to go more in depth while reading these papers. Now, first thing I want to mention, all these 3 papers by OpenAI, very revolutionary. I really love this subfield of post-training. I feel like it prompts a lot of questions, and it prompts a lot of thinking on what intelligence truly is, right? Another thing I want to point out, these big papers, all 3 of them, they have very notable names. Particularly, you might have seen this name, Alec Radford. I believe he is also in this paper, Learning to Summarize. And in the 2022 paper, he's not there, but Alec Radford, he's actually the author, one of the primary authors of a bunch of really important deep learning papers. Right off the top of my mind, there's language models are few-shot learners, which is basically the GPT-2 paper, I believe. basically or GPT-3, basically showing that scaling these models up results in a lot of incredible intelligence capabilities. The other one is CLIP. This has nothing, well, it kind of has to do with large language models, but it's more into the field of computer vision and multimodality, in which you take two encoders, text encoder, image encoder, throw them into the same latent space, and now you have a model that actually understands what it's looking at. Well, he was part of all this. We also have Paul Cristiano. He is in all three of these papers. Where is he? Right here. So you see the team at OpenAI was cracked, back in the day when they were working on these papers. There's also one really big name here, Dario Amodei. He is actually the CEO of Anthropic. So he wasn't in this last paper because by then Anthropic had already branched out from OpenAI. But it's really cool and interesting just looking back at all these names that have worked on these papers and how all of these people have revolutionized large language models. But enough yapping. Let's get into it. First thing I'd like to do is read the abstract of this first paper, Fine-Tuning Language Models from Human Preferences. Now, we're going to see the differences in the three papers and how each one builds upon the other. This paper effectively introduces the idea of reinforcement learning from human feedback by using PPO. However, a lot of the ideas they present weren't exactly finalized. You can see there are very primitive approaches to what we do nowadays. But again, let's go into it. Here they talk about how reward learning enables the application of reinforcement learning to tasks where reward is defined by human judgment. The whole idea of using reinforcement learning in something like this is just the idea that it is very expensive to create a perfect response for each potential prompt. There are an infinite amount of prompts that we could give a model. So we can't have a perfect data set that has golden answers for each thing. So we have to fall into this RL environment where, given a prompt, we produce multiple responses and then have just humans choose which one they prefer most. And from there, we kind of create this data set. Now, most work on reward learning has used simulated environments, but complex information about values is often expressed in natural language. So they claim in this paper they build on advances of generative pre-training, what we talked about at first, to apply reward learning to 4 tasks: continuing text with positive sentiment, physically descriptive language, summarizing, and yeah, those 4. Now, in the introduction, they talk a lot about previous work on reinforcement learning. Such as here, and you see all these references, right? Much of this work uses algorithmically defined reward functions, such as BLUE and Rogue. Algorithmically defined reward functions, that's basically what gives us the actual reward given a step in the environment. Here, they use a whole other language model, a reward model, that outputs a scalar value. This is really interesting. Just wanted to point that out. Music theory-based rewards. I don't know how that works. If you guys are interested in looking that up, I mean, here's the reference, but weird stuff, I guess. But yeah, here they just talk about previous work. But let's look at these graphs. I mean, why look at a bunch of words when you have these beautiful graphs that help you build an intuition of what's actually going on instead of these big, like, mathematical phrases and whatnot, Greek letters, all that. As you know, from the past now we have experience to actually understand what we are reading. The policy model if you remember from PPO, that is the model that actually performs the actions and outputs a probability distribution of the actions. Or in an actor-critic setup, it is the actor. And the reward model. We've talked about the reward model before. We might go more in depth on it in this same paper. But here you see basically the training process for this comes in 3 steps. Or well, 2 steps, right? First, we have to train a reward model that knows, given a prompt X and a response Y being fed into the model, here's the model, it learns to output a scalar value that basically defines whether the prompt or the response for the prompt was a good one or a bad one. How does it know this, right? We have to feed it a data set of a prompt with all the different responses and then what the humans picked. And from there, we perform this loss from this model called the Bradley-Terry model. We're going to see it later today, where we just basically quantify this, learn to quantify this in a way that this model learns to output, let's just say, keep it simply, a positive value for a good response and a negative value for a bad response. Now here, you see, we give the context to the policy. This is the X. Think of it as the prompt. Pass it through the policy. And we have 4 continuations. So that's a Y1, Y2, Y3, etc. Passes to this reward model who gives 4 rewards. And that is a loss, given the human label. Now the human label is just the ranking. And we mash these together for the loss, and that's how we train this reward model. Now, once this reward model is fully trained and it's really good at telling what a good response is versus a bad response, we now train the policy. Because now we want the policy to produce good responses all the time, basically. Instead of just here, it produces 4 random responses and we grade them. So here we have a continuation. Again, this is the Y. We grade it, and then we use this reward to update the gradients of our policy. Now, you might be wondering how this loss is connected to this policy. This is just a policy gradient method, and we're going to talk more about that. Here they go mathematically into it. This is why I kind of wanted to avoid this. Like what, bro? What are you doing? You know what I mean? It's a lot of math-looking things, and it might be scary at first. Now, intuitively, it's exactly what we spoke of. So no need to worry about that, right? Just learn it, kind of read it in depth, but don't pay too much mind to this stuff. I mean, this is just a probability distribution over sequences of tokens. That's just how a language model produces a next token given the past tokens produces a next token, probability distribution. Then there's ways to select the highest probabilities from there, but yeah. Now we have the input space X, data distribution D over X, okay, and output space Y, whatever. In the case, for example, that we are working on summarization, which is kind of what they talk about here, we have an article. X is the article of 1,000 words, and then the response Y is the 100-word summary. And then we just basically, a policy is kind of figuring out the probability of Y given the input X. So what they first do here, they talk about initializing a policy pi equals P now, and then they fine-tune pi to perform the task while using RL. That's basically exactly what we're talking about right now. But the definition of the reward function, R, is this. It's basically what this means is that the reward function is the same as the reward model. Effectively, these neural networks, they're all just big functions, right? So R is, what this is saying right here is R takes X and Y as input, and it outputs a real number. That's just saying that literally what we did up here, where we take x and the y and we output a scalar value. This is just the mathematical speak for that. And we want to optimize for the expected reward, right? So given an x out of the data set and a y out of that is produced by the probability distribution of the policy given x, we basically want to optimize this reward. But again, the only way we can do this is by asking humans what they prefer. And so, like we talked about, we choose between 4 options. And we're going to go more in depth on this in the future papers and why this kind of was ditched. At the beginning, I mean, if you see now, it's very rare. I don't think you get it at all, where you get a prompt or where you give a prompt to a model and then you're given like 4 responses to pick from. No, that's too much cognitive overload for a human. So we kind of, from this point forward, after this paper, we kind of just reduced it to 2, and that's basically what you see in your ChatGPT chats and Gemini, all that. There's situations where they give you 2 prompts, and you kind of, select one, ignore the other. And what they do is create this tuple, this data set that is created of the prompt, the 4 options, the 4 responses, they call it completions, and B, which is the option that is selected as the best one. So out of 0, 1, and 2, let's say we have prompt X, which is like, what is a car? Y0 says that a car is like a metal machine. Y1 says that a car is an animal. Y2 is says that a car is a mechanical machine with 4 wheels, and Y3 says that cars are made in Europe. B would probably select this one as the best one, so here the B would be 2. We're just giving, out of those 4 options, which one was the best one. And our loss is, in this case, our loss of the reward model is basically a softmax that basically gives you a log probability of the correct y over like the rest of the y's. This is a softmax here. And yeah, so we do that a bunch. We basically feed the reward model this tuple, and what we wanted to do is, out of y0 to y3, let's say again it's 2, that was the best option. We have y0, y1. What we want to do is bring the probabilities of these down, the token probabilities. Same thing with y3, bring these down, while the response y1 or y2, the probability of y2 going up. And it's normalized, mean 0, variance 1. You see that a lot in reinforcement, or sorry, in deep learning. And now given that reward model, what we do is we have an extra step here that we don't see in PPO, and it is this equation right here. It's a modified reward. So now I'll explain this here. 1 second. So what PPO, if you guys remember, PPO, right? We have our reward, but what exactly is this here? This is what we call the KL penalty. And what you basically see here, I'll explain it. We have this hyperparameter beta. which we initialize. But what's more important here is this ratio. We have a ratio. If you remember, clip has its own ratio, PPO has its own ratio that's clipped. But this is on top of that. We want to kind of modify the reward. Reason being, we don't want the probability distribution of our policy that we're training to diverge from the original model with its pre-trained capabilities. What does that mean? Basically, what you see in a lot of situations is that we fall into this habit of reward hacking, which is a term that they use, where the policy model learns basically to hack its way to high rewards without actually producing good outcomes. Now, the way we limit that is we kind of want to create a measurement that shows how close the policy that we're training is to our old policy, our pre-trained base policy. And we don't want this ratio to get too big. Whatever this ratio is, if it's a very high ratio, what we do is we subtract it from the reward, so we don't give too much reward to the reward hacking, if that makes sense. So here they say we choose a constant b, which is the hyperparameter, or vary it dynamically to achieve a particular value of KL. It's KL penalty. The term has several purposes. It plays the role of an entropy bonus, which prevents the policy from moving too far from the range where the reward is valid. And so what the whole process basically is, this is the whole loop of it. We gather the samples. This is kind of the data set creation. And then we initialize the reward model to the base policy and replace the final layer. Instead of being size, vocabulary size, we do it for a scalar. And then we train this on the human samples. And then we train our policy via PPO with this reward model. So you can imagine our environment. What gives us the actual reward is the reward model. And then, in online data collection case, we continue to collect additional samples and periodically retrain the reward model. Online basically means that during training, we still collect newer data, and then we, as you see here, it's kind of a form of continuous training where we retrain the model with the additional samples, and then we keep this going. Pre-training details, they use GPT-2. I mean, nothing extraordinary here. It's just GPT-2, a normal language model. Fine-tuning details, I think this is important to understanding for when we build, but basically from here we could jump straight to the results of this and kind of how this impacted the field back then. So fine-tuning details, starting with the pre-trained language model, the reward model is trained using Atom with loss, an equation somewhere there. Batch is 8 for style tasks and 32 for summarization, learning rate. All right, this is just good for understanding how they trained it themselves. Now, actually, they only trained one single epoch to avoid overfitting with no dropout. So the reward model is already a pre-trained transformer. You just train it one more time on one epoch on the new data. And then for the training policy, they use PPO2, basically just PPO, the PPO that we know and love, using 2 million episodes, which are 2 million XY pairs, lambda equals 1. Did I say lambda? I meant gamma. And 4 PPO epochs per batch. Again, we've built this last video. We understand what PPO epochs are. This is just in a language model scenario. And now if you see here, this is our clipped objective again, where we clip this ratio with the epsilon range. Now, what did this result in? What did this show? There were interesting findings here. Let's see if there's anything worth discussing. Yeah, here they talk about online data collection. Again, it's what we talked about here, where they continuously train the reward model. Human labeling, Scale AI labeled everything through an API. Interesting stuff. You could find stuff there. This is an interesting finding that there was a low rate of agreement between what the authors thought was a good response and what the labelers thought was a good response. This is a persistent problem going into the future across all three papers. Because again, human preference is really noisy, and it comes down to a lot of things, what one person prefers as a response compared to another. And it does raise questions, kind of the models end up reflecting the people that actually, obviously, I mean, the data is what's most important in any of these models, ends up reflecting the values of the people that prefer the responses. Interesting stuff. And so you see in future papers, they kind of put these really tight or tighter guardrails on what a person can label as a good response. So it's kind of philosophically, it's weird, and it's something to give some thought into. How much hands-on control preferences must be, how much hands-on control must be placed again on top of someone's preferences before you're just getting like a really biased data set. But yeah. And experiments, they tested on TLDR data sets. This is going to be really important because that's basically what this paper is all about. Daily Mail, what was the other one? It was like, let's look at the responses actually. Oh, it was stylistic continuation, right? In front, KO versus mock reward. And so here you see examples. Here, allowing the policy pi to move further from the initial policy was measured by KL, achieves a higher reward at the cost of less natural samples. Here we show the optimal KL versus the reward using PPO, 2 million episodes, whatever. Now the code actually works for only for the 124 million parameter model, which we built ourselves. It's on this channel, built it with my good friend, and I'll probably link it. I don't know how to do that though, so if it's not linked, I'm sorry. Whatever. It's called the GPT-2 in JAX video. Anyways, mock sentiment tasks, you kind of see what they work with. And they do a lot of tests on offline training versus online training. And they kind of see what labelers prefer, what model the labelers prefer. And yeah, I mean, from here, you can just see kind of what they worked with. They give some context and then zero-shot continuations. Here's just continuation. Hello, I'm Pro, and this is my friend Mike said Pro, whatever. That's what the model continued with. We also have, where's the descriptive ones? These are summaries. And it's just comparing zero shot with the fine-tuned with supervised, like SFT, and then this what reflects modern RLHF. Again, here they didn't have a paradigm yet. They were still discovering these things, so they are still comparing what each thing works amongst them. Yeah, I mean, you find interesting stuff around here. I'm not really going to go too deep into this. I think I've already spent a lot of time. Maybe challenges. Challenges, again, what we spoke of the most, kind of what stands out to me the most is the quality control. Like, yeah, this whole idea and this whole concept. Again, this is what makes post-training such a big field that requires a lot of research, because we're trying to find a way to mathematically find the best human-like responses, but human-like responses can mean anything to anyone. And yeah, I mean, we're going to read the conclusion a bit. We demonstrated RL fine-tuning to 4 NLP tasks. Our results were mixed. Continuation tasks, they achieved good results. But for summarization tasks, the policies were only smart copiers. Yeah. So you could go ahead and read this paper, go more in depth on it. I'm going to jump to the next one. This is fine-tuning 2019, fine-tuning language models from human preferences. But on to the next one. Here we have learning to summarize from human feedback. Here they push it forward and they're like, okay, this is a cool approach, RLHF. Let's ultra focus on summarization, which, I mean, if you recall, it's actually one of the things that this paper said that they failed at. Let's jump into summarization and let's see how it works. Right here. And so the abstract states that it's kind of a similar thing. Language models become more powerful. Training and evaluation is increasingly bottlenecked by the data and metrics. Summarization models are trained to predict human reference summaries and evaluated using Rogue. And then in this work, probably most important sentence, I guess. Yeah, we show that it is possible to significantly improve summary quality by training a model to optimize for human preferences. Same thing, just ultra focused on summarization. And here you see what's up. This is the models humans prefer. You see the pre-trained only baseline. Here we have the sizes of the model. Pretty good. Not good. I mean, 0.3, that's not good. But supervised learning, which is the SFT step, which is explicitly shown here and I'll go more in depth on, shown a little better, but human feedback is where you really see improvements. So the main contributions is that they show that training human feedback outperforms very strong baselines on English summarization and generalizes much better to new domains than supervised models. That's actually something interesting and another big reason for PPO, for the use of reinforcement learning. When they're talking about supervised learning, supervised models, SFT models, is that after they have the pre-trained base, they feed this model a bunch of prompts and a golden response, like literally written by a human golden response. Now, the thing is, with this, you can imagine how expensive it is to have someone write for every situation a perfect prompt. And then also when we post-train a model on that, and when then we give it a new task, it still has no real understanding of how or of what a good response is. So this is a good starting base, but it's not generalizable. That's why reinforcement learning helps a lot here. They find that or prove that here in this paper. Conduct extensive empirical analysis of our policy and reward model. Examine the impact of model and data size. Cool. And then release human feedback data set. Awesome. Open source. Perfect. And so high-level methodology. In this paper, they start going more with the approach of given a prompt, they just give 2 responses and then a human picks one and just avoids the other. We start with an initial policy that is fine-tuned via supervised learning on the desired data set. Again, what we talked about. Step 1. Collect samples from existing policies and send comparisons to humans. This is this step right here. Learn a reward model from human comparisons. Again, same thing we talked about in last paper. They're just reiterating it. And train a reward model to predict the log probs that this summary is the better one. And then we optimize a policy against the reward model. Here's what it's shown. The other paper actually has a very similar, just straight up a very similar approach to this. It's almost the same thing, but now they like pushed it heavy. Now, why is the paper missing this third thing? Hello? Okay. First thing you do, they collect human feedback. In this case, it's the Reddit posts and the Reddit summaries. And then the human decides which one is better. Cool. We train a reward model with this loss right here. Much simpler loss, might I add, compared to the other one. The other one had the tuples and this and that, and it could have gotten a little confusing. Here, our loss is literally just the logarithm of the sigmoid function. God, that was bad. Sigmoid function. Damn, I actually forgot how I wrote the sigmoid. There you go. Of R, the response I, or J, sorry, minus response K. Yeah. They basically see the separation, put it into a sigmoid, which is between 0 and 1, and the logarithm of that. And then this new post is sampled, or this new thing is used to train our policy using this reward model. Same thing we've talked about. I hope it's making intuitive sense, honestly. There's nothing overly confusing about the approach. What's more overly confusing, honestly, we've already done, which is PPO itself and the algorithm itself, and understanding the hyperparameters, the use of a critic to grade each step. And honestly, this is all going to get more wrapped up when we actually implement this RLHF pipeline ourselves. But I think it's a very intuitive process, honestly. Again, they have the reward model here. Look, this is the best thing in the world right here. Now we have a clear loss. And at the end of the day, this is the Bradley Terry that I was talking about. This is the loss that we use now forever. No, I shouldn't say that. I shouldn't say that. This field moves very fast, but intuitively, this is a very good loss function. So we give the model yeah. So we have y0 and y1, right, given a prompt. We have y0. Let's say y0 is 9, and then y1 is like 6. What we want to do is basically get these numbers as far apart as possible. Y0, let's say, was the good one, and this one was the bad one. What we want, basically, in a way, let's say we normalize it with a mean of 0. We want this to produce a negative number, and we want this to produce a positive number. Now, if they're this close together, right, 9 minus 6 equals 3. 3, we do the sigmoid of this, and this loss basically tells us to kind of push these apart, I guess. A well-trained reward model will produce a 9 for the good one, but then like a -6. So then when you do 9 minus -6, you end up with 15. That's much bigger. And yeah, the sigmoid of that gives you some value. And then we find the logarithm of that. Just making sure real quick. Something might be like a dumb thing to look up, but yeah. So then what this gives is a negative number. The higher the better, I think, in here. The higher the better. So that's what's important here. And then we see, how do we update the actual reward? Well, we have our reward. And then we basically do the KL penalty again. With the SFT base, which is basically before we started the reinforcement learning, and then we have the RL based. Now, an important thing to note about this paper is, let me see if I find it here, because I definitely skipped over it, but it's just the idea and their focus on basically on how they train this offline. You saw how they talked about a lot about online training in the first paper. Here, you're going to see that they train offline mostly. So the reward model doesn't get like continuously trained throughout with new data. Right here. First, we transition entirely to the offline setting. If you remember, this was actually a big issue here. Where is it? Oh, it was literally this whole quality control issue. Bypassed, they said, let's just do it offline. Where they send large batches of comparison data and then retrain our models on the cumulative collected data. And then they maintain a hands-on relationship with the laborers. That's what we were talking about beforehand, where they literally give them instructions, answer questions, and provide feedback on performance. Obviously, that's needed, but always important to flag this. You like the flag? Always important to flag this of how noisy human data is. Human preference data. And so the results, the policies trained with human feedback were largely preferred compared to the supervised policies. And summary length, how do I, whatever. Yeah, you see the quality of the human feedback was a lot higher, especially here. See anything more important? Yeah, I mean, this paper pushes on the claims and shows that this can work for summarizing as well. I'm not sure what more I can show you guys here. I would really suggest you guys read this on your own as well. But here, let's again go through the limitations. One limitation of our work is the time and cost required to produce our final models. Fine-tuning 6.7 billion. Yeah, so they definitely scaled it up. But yeah. Then introduce Instruct GPT. Hey. Okay. Instruct GPT is famously a model that was 1.3 billion parameters, and it was preferred. Like, people preferred the outputs of 1.3 billion parameters to 175 billion parameters of GPT-3. It's probably the biggest thing from, I guess, what made this paper so special, that a 133 parameter model beat out a 175 billion parameter model. That really showed to a huge scale how much reinforcement learning really helps with this. And here they talk about, kind of introduce the whole concept, not introduce, but formalize the whole concept of alignment. We show an avenue for aligning language models to user intent. Same process, labeler written prompts and prompts with submitted through the OpenAI API. Fine-tune GPT-3 using supervised fine-tuning. And then they use RLHF, instruct GPT, and yeah, super cool. So here we see the comparison, very similar to the first one, but now just generalized. Now we have we're using it for different scenarios, not just summarization. We have GPT, just base GPT, horrible win rate. And I love the concept of win rate. You're going to see now, instead of here, it was RJ and RK. Now we have RW and, YW and YL. And now in my heart, what that means is Y winner. Probably what it means. But I haven't really seen anything from that. My code has Y winner, Y loser. Just the response people preferred versus the response people did not prefer. Anyways, here we have our base GPT, very bad. Low win rate, not good. Here we have GPT prompted, does a little better, especially at higher parameter counts. This can probably be attributed to bigger models having larger intelligence capabilities. Then we have our supervised training base, which is basically where our policy starts from. And then we have PPO and PPO PTX. I'm going to be honest. I don't know if PPO PTX is really used that much nowadays. I mean, this doesn't show incredible improvement. We'll read over what it is, but just kind of bunch these together. You see PPO does much better than the other methods. And so, I mean, we see the same thing here. Explain the moon to a 6-year-old. Here we collect the data. And then we train the model with that data. Findings here. Labelers significantly prefer instruct GPT outputs over GPT-3 outputs. We talked about that. Show improvements in truthfulness over GPT-3. Twice as often. That's good. People definitely choose and prefer truthful. And well, I'm not going to say people prefer truth over false, but for a language model, they prefer that they're being told the truth and not being like lied to, I guess. Small improvements in toxicity, but not bias. Actually, I have no idea what this, or I can infer what this means, but I honestly haven't read it into it. I'm gonna read it now with you guys. And then minimize performance regression on public NLP datasets by modifying the fine-tuning procedure. Let's see what that even means. Regression, we observe performance regressions. This is the PPO PTX. So we greatly reduce the performance regressions on these datasets by mixing PPO updates with updates that increase the log likelihood of the pre-trained distribution. I mean, in a way, the way that I see this and the way that I interpret it, I'm gonna be honest, I don't have a full grasp of this one, but the way I interpret it is basically a whole other layer of preventing drift. And so a big common theme is that idea of ratios. PPO has the clipped ratio. Doesn't allow the policy to move too far from its older state. RLHF has the KL penalty, penalizes the reward given how far the policy is from the base supervised fine-tuned model. And then here, we increase the log likelihood of the pre-training distribution every once in a while. I guess in a way, this is to maintain its pre-training capabilities even more so than this KL penalty does. Our models generalize the preferences that held out labelers did not produce any training data. With held out labelers, find that they prefer InstructGPT. Okay. However, more work is needed to study. Okay, I wouldn't pay no mind to this one. You see a lot more focus on generalization. So you could literally think this as like the final boss of these two papers combined. Generalization instructions outside of fine-tuning. That's perfect. And I think this is the most beautiful part. This is probably what, just a huge finding here. InstructGPT models show promising generalization to instructions outside of the RLHF fine-tuning distribution. So they've probed the capabilities on questions on code, summarizing code. As I talked about at the beginning, here we're seeing that push towards more quantitative. I don't know exactly what, more like logic-based, mathematically based, and inclined subfields of the world. And yeah, a lot of talk on harm. Again, this paper kind of generalized, formalized the idea of alignment. And focuses a lot on generalization. I'd say these are the two most important things I can get from this paper, because this is basically, I mean, that's basically the point of RLHF. We want the super duper human-like, smart, nice, kind, truthful model. Yeah. Methodology, bruh. Again, collect the demonstration data, collect the comparison data to train the reward model, and then PPO. That's it. So when we build this, we have to keep this in mind, those 3 steps along with PPO. If you remember, a couple things. We have 3 steps. So step 1, data collection, whatever. Step 2, reward model. Step 3, PPO. And what does PPO have? PPO has the 2 steps that we know about, the rollout and the updates. We're forming a more unified theory and understanding of how this works, which is the best thing you can do. Awesome. Data set, plain, free shot, user-based, cool. I'm not going to spend too much time here. See if anything important. Let me check my notes if I'm skipping over anything at all. Yeah, I'll talk about this. So yeah, supervised fine-tuning, train for, here they give the stats, cool. Loss for the reward model, why winner, why loser. They have this. And you see this -1 over k choose 2. What k choose 2, it just label this for you guys. K choose 2 means, well, this is equal to this. I believe this is some combinatorics focused thing. And what this basically means is this is counting the number of ways to pick 2 items from a set of K. So the reason is this, you could kind of think this again, everything here is like final boss. So this is basically the final boss of what they were doing before, where they were having 4 scenarios, or 4 responses, 2 responses, all that. What they decided to do here was present 4 to 9 responses to rank, and then that produces number of ways to pick 2 items from a set of K, right? So from there, we have, let's say it was 4, we have times 3 over 2, we have 6, we have basically 6 pairings of a Y winner and a Y loser. So that's a really interesting thing, because from there, you basically take the best of both worlds. You know, the loss is much simpler with having a winner and a loser, right? But also you want more, bigger data distribution. You want more data. You don't want it to be stuck in its, with a limited data set. So how do we bypass that? We just give in a prompt. We have 9 responses, and we find a bunch of ways that we can create pairings out of those 9 responses, or 4 responses, or all that. I mean, if we do 9 responses, oh man, I'm not good at math, am I? 36. Yeah. Yeah. We have 36 different pairings. From one prompt, we produce 36 pairs that we can train with. Instead of from one prompt, we just have 1 pair. That's awesome. That's cool. So that's basically what this is all about. We know this. Yeah. And then reinforcement learning. This is the PPOTX stuff. But again, here you basically see the same thing. And we're going to talk about implications now. We have the reward. We subtract the KL penalty. We don't want this to drift too far from this. Plus this. What the heck? Yeah. And this is basically the PPO PTX stuff. I wouldn't pay too much mind to it. And honestly, again, I don't get it too much myself. Or not that I don't get it. I have an interpretation of it, but it's not the most confident. But yeah, and then you see results here. Same thing. I mean, look how close these are. In fact, in the majority of them, I even see PPO just beating out PPO PTX. So I wouldn't say it's something worth fussing over, at least not as of this paper. There might be some paper that dives more in depth on this, and that is worth looking at. And everything in every data set, you see that PPO kind of just does better. But let's focus more on how exactly we can build this. And my focus would be straight up on the loss. Okay, perfect. They don't really talk much about the critic, but you're gonna see it here. I mean, you see that this KL penalty is done per token. See how I can explain this. Let's talk about the models that we have. So we can understand RLHF PPO better. So we know that PPO has an actor and a critic. Now, we know that the actor is the policy. Now, the policy is a full transformer. Full transformer it has an output layer of like vocab size, because what it outputs is the probability distribution that the next token is what it is, whatever. We also have a critic. Now, what the critic does, as we know, a critic estimates the value. Let's just call it the value model. It's also a full transformer, but the final layer outputs it outputs a value for the token. So that is a scalar, except it's batched. So you can say it's like batch like this. But if you guys remember, the value basically helps us compute the advantage. And the advantage is what tells us whether that step that we took in the environment was better than average or worse than average. If you remember in PPO, these two are trained at the same exact time. In this case, what this does is it calculates the per token value. And then we already know of the reward model, right? Again, full transformer. Now we have 3 models at the same time. And what this outputs is the reward, the scalar reward. Given, if you remember, given a prompt X and the response Y. And then think about this. How do we compute this KL penalty? I mean, we do need the base, right? So yeah, that's what we call the reference model. That's what we call the reference model, which is another full transformer built upon this policy right here. So another full transformer. So RLHF, we have 4 models at the same time in memory. Think of the overhead. This is something engineering-wise is very hard to deal with, and I'm actually struggling with that right now as I'm building my RLHF pipeline from scratch in JAX. I'm just having a lot of trouble maintaining these all in memory. But you can see how hard it is to kind of train this. So now what we have is 2 models. We have the frozen model, the frozen models, right? These don't get trained. These are offline, right? This reward model was trained by itself. Single epoch in the first paper. This paper, could look for it. But let's focus on this for now. The reference is just the frozen SFT model. So that's basically the policy before it was even trained. Same weights, same everything. And then these are trained online. Get a more separating color, yeah. These are trained online. Because as you know, with PPO, these two kind of feed off of each other and they get trained at the same time. So just think about how heavy that is. I mean, we have 4 of these in memory. If one is a little off, the whole thing goes berserk. And this is reinforcement learning we're talking about. When something goes wrong, it's over. You know what I mean? Like, everything has to be on point. Just keep that in mind for future improvements on PPO, which we're going to talk about, especially, namely, I guess it's a little wink wink intro to the future, but mainly DPO and GRPO. But that's future stuff. But yeah, I hope you guys enjoyed this video. And I hope you guys formed an intuition of what RLHF is and finally have that understanding of it. Again, throughout all this, I focus mostly on the RLHF aspect of it, on this part. So we understand how these models are post-trained. Next video, what I'm going to do is, I'm going to draw out exactly how PPO works in this process. I mean, you guys have built PPO in the past. We've done it together. So we know how PPO works. There are a couple little edits we have to do, of course, to include this reference model for the KL penalty. But as an exercise, just try to try to think about how PPO connects to RLHF. And next video, I'm going to draw a diagram that essentially reinforces the idea. And then we are going to build RLHF pipeline, PPO, using JAX. And that's probably going to be a very long video. But it's also a very incredible project, and not many people probably have done this. So again, your intuition goes through the roof on how these things work. But I hope you guys found something of value in this video. I hope you guys could take away something from this. Let me stop sharing my screen. Again, I hope you guys found something of value in this video. I know it might have been long, a longer video, 3 papers, maybe not the most exciting stuff, but next video and next episode in the series, we're going to straight up build that from scratch. And we're literally going to own the post-training pipeline of modern AI. We're going to own it ourselves. And that is something incredible. So I'll see you guys next video. Thank you guys so much for watching, and I'll see y'all then.